welcome to the first afternoon session of this joint workshop. It's a session on categorical quantity mechanics. Our first speaker is Selinger, and he tell us why and how finite-dimensional Hilbert spaces are complete for dagger compact closed categories.
Thank you very much. So it's a bit of an unusual QPL workshop so far because there have been 3 talks and no one yet has talked about Cook's compact closed dagger.
I was the title of his talk.
So I'm going to do that now, and I guess so I have to kind of tell you sort of briefly what they are. Now what I want to show is that, so there's this graphical language, okay, that many of you have seen that Bob Cook likes to use and I like to use and other people like to use it. And what I want to prove here is that an equation holds in this graphical language if and only if it holds in finite-dimensional Hilbert spaces. So it's a kind of representation theorem or completeness theorem. It's useful because, of course, we know the opposite. Like we know that we can interpret the diagrams in the Hilbert spaces, but it's nice for counterexamples to also know that if if you want to check that some equation fails, it suffices to do that in a finite-dimensional Hilbert space. So this actually is, I would say, like more than probably 80% of this work was done by Hasegawa, Hoffman, and Plotkin, who proved the corresponding result for traced monoidal categories and with respect to finite-dimensional vector spaces. So the little epsilon that I've added to this is just to do it for dagger traced monoidal categories, and then you get the corresponding result for Hilbert spaces, where we foresee the Hilbert structure to interpret the dagger, the adjoint of an operator. And I've also, I think, my proof is also simpler than theirs. So even if you specialize the proof back to without the dagger, you still get a simpler proof than the proof that they have. So that's maybe also a contribution. There are different kinds of categories that people talk about, and if you're not a category theorist, you probably find these confusing and maybe not necessarily care that deeply. There's something called a traced monoidal category, there's something called a compact closed category, and for the purposes of this talk, all you really need to know is that if you can prove the theorem for one of them, then it immediately follows that you can prove the theorem for the other class. So it doesn't much matter if you say compact or traced. So I will only talk about the traced case here. So a category is given by a class of objects and then a class of morphisms between them. So you think of the objects as sets and the morphisms as functions, or you think of the objects as spaces and the morphisms as linear functions or linear continuous functions or something like that. Now a category is said to have a dagger structure if for every morphism from A to B, or let's say if there's an operational morphism, right? So that's F dagger goes from B to A. So a typical example is the adjoint in Hilbert spaces. Right? And it has to satisfy some obvious equations, so it has to be involutive and functorial, and the dagger of the identity has to be the identity. And interestingly, already in such a simple structure as a dagger category, you can define a lot of concepts, such as unitary, for example, or self-adjoint. These concepts make sense in any dagger category, which could be a category that is completely different from Hilbert spaces. For example, the category of sets and relations is an example of that's not at all like Hilbert spaces, but which has this structure. Now, a symmetric monoidal category is just terminology that refers to a category equipped with a tensor product. So you can tensor any 2 objects together, the kind of thing that we just heard in the previous talk. And then we say that the tensor product is compatible with the dagger structure if it satisfies a bunch of properties here. So you tensor to get. So first of all, you not just have tensors of spaces, but you also have tensors of morphisms, right? So if F is a morphism from A to B and G is a morphism from C to D, then F tensor G is a morphism from A tensor C to B tensor D. Right? And then the dagger of the tensor has to be the tensor of the daggers, and the associativity maps have to be unitary, and the left and right map for the unit of the tensor product has to be unitary, and that's called a dagger symmetric monoidal category. And again, Hilbert spaces are sort of the most a typical example of that. But again, sets and relations also works. Now, so I will not actually talk about dagger compact closed categories, which are the kind of categories that Abramsky and Cooke defined. But here I will take a simpler notion called a dagger trace monoidal category. So you have the dagger and the tensor product on your category, and then you also have a family of trace operations, which means given a morphism from A tensor X to B tensor X, you can apply this operation to it and retrieve a morphism from A to B. Okay, it's called a trace because if you do that in vector spaces, it's actually, what's normally called a partial trace, right? You trace out the X by summing over the internal index. So in particular, if A and B are not there at all, then it just gives you a scalar as the answer, right? If A and B are the trivial space. And for the trace structure to be called a dagger trace structure, it then also has to satisfy this additional axiom. Here you can quickly check that is true in Hilbert spaces, that if you take the trace of the adjoint of an operator, it's the adjoint of the trace. And so every compact closed category of Abramsky and Cooke is an example. This is a slightly more general notion. Now, I didn't really write down the axioms very carefully, and even if I did, you probably didn't care to read them so carefully. And the reason you sort of can gloss over the axioms is that these kind of categories have this very nice graphical calculus associated with them. So, and then there's a completeness theorem telling you that an equation follows from the axioms if and only if the corresponding graphs, when you write them down, are isomorphic, so that you can actually reason from the graphs. In some sense, you don't need the axioms because you could take what I just said as the definition of the equation of a trace dagger, whatever category, right? Okay, so an object will be represented as a wire, a morphism will be represented as a box. Everyone has a different convention. Some write the wires from right to left, some write them from bottom to top. I write mine from left to right. And I put a little mark in one of the corners of the box. That's so that we can later tell if we've taken the mirror image of something. Right? The identity is just a straight wire. The composition is just writing boxes next to each other and connecting the wires up. And the dagger of this morphism here from A to B will be represented like this. So a morphism from B to A, which is actually the mirror image. We will take it as the mirror image of the other one. So if you take the dagger off just the box, then all that happens is that the blob moves to the other corner. But if you take the dagger of a whole diagram that's made up from several boxes, then you have to take the mirror image of the whole diagram. Right? And of course that also changes the role of A and B, and somehow my notation has arrows on the wires that I probably should have omitted because they always run from left to right. Alright? And so that's 5 of the things, and just because all 8 don't fit on a single slide. The slide, I still haven't corrected this typo, which has been in this talk, I'm sure, for at least 3 years. The tensor product of F and G would be an F here and a G here, right? So the boxes written next to each other. The symmetry is represented in the obvious way. And the trace, which is the most interesting operation. So given a morphism from A tensor X to B tensor X, you actually just connect the wires in a loop, right? And you get a morphism from A to B. So that's the graphical notation of a trace. Traces are also used in computer science a lot to model things like recursion and iteration, loops. Okay. Of course, here the wire sort of briefly travels from right to left. But the point is, in a traced monoidal category, it can only be attached to a box when it travels in the left to right direction. It's allowed to travel backwards freely, but there can't be any boxes along the way up here. Right. Boxes can only be in the left to right direction. That is, by the way, the difference between the traced categories and the compact closed categories, where you can have boxes everywhere, even on the wires that travel right to left. Okay. And now there's this important theorem that actually only special cases of the proof appear in the literature. but everyone believes this theorem to be true. Okay, so the percentage of this theorem that has been proved follows from these 3 papers there. My contribution is again very small. It's just the dagger part, and that's almost trivial, right? Once you have the theorem without the dagger, it's just an observation. It also works for the daggers. But the theorem is that a well-typed equation between morphisms in the language of dagger trace monadic categories follows from the axioms that I didn't actually show you, if and only if it holds up to isomorphism in this graphical language. So that's it, and we're going to use that. Now, what I want to prove today, there's supposed to be a slide somewhere showing the main result. Here it is. Right, so let me start with the main result again, which is really stated in an awkward way here. I'll just say it, right? I want to show, we already have, it follows from the axioms if and only if it holds in the graphical language, and now I also want to show if and only if it's true in finite-dimensional Hilbert spaces. Right. And when you think about how you calculate in finite-dimensional Hilbert spaces, for example, when you think about how you calculate matrix multiplication, there's this summation of internal indices formula, right? If you multiply 2 matrices, then you're summing over all I, right, where I ranges over some orthogonal basis, let's say. And when you take the product of 3 things, then you're summing over all I and j, right? And I and j are the internal indices here. And then if you take a trace of ABC, and I did somehow, my LaTeX always crashed when I tried to put the diagram here, but it would be ABC with the trace, right? Then you're summing over all 3 internal indices. So the indices are, it doesn't matter if a wire is a trace or if the wire is just a straight wire. The summation formula is exactly the same. And it's of course the same that you called half integral this morning, or, you know, in your case the space was 2-dimensional, so you were summing over a Boolean, you call it Boolean variable, right? But it's just a, just that. Of course, the basis independent, right? The actual result of the summation. So I want to show that 2 terms in the language of dagger trace monadic categories are equal for every possible interpretation in finite-dimensional Hilbert spaces, if and only if it holds in the graphical language. We already know that that's the case if and only if it follows from the axioms. I only wrote the if-then part here because, of course, the opposite is already trivial. We already know that Hilbert spaces are dagger trace monadic categories, so obviously everything that the axioms say holds in there, right? We're only interested in the opposite direction. Alright, now to prove this result, it suffices without loss of generality to consider a special case. Okay, I'm going to specialize it in 2 particular ways, and I'm going to say why it's without loss of generality. First of all, it's enough to consider morphisms that go from the tensor unit, so think the base field to the base field. Okay, so that would be diagrams that don't have any open wires, right? Diagrams where everything is closed up. Why is that sufficient? Because if you had a general morphism, say from A tensor B to C, then you can introduce a new variable from the base field to A tensor C, A tensor B, and another new variable, which is a morphism from C to the base field. And I wish I had a blackboard that I could write on simultaneously. Maybe I should just sort of not. Well, think of a diagram that has a bunch of wires coming in and a bunch of wires coming out. Now, attached to all the incoming wires, just a big new box labeled F, right, where F is some variable you haven't used. And attached to all the outgoing wires, another box called G, where G is some variable that you haven't used. Then use the theorem for the closed case, and finally say, well, if that equation holds for all F and G, then of course, obviously, the original equation also holds. So that's without loss of generality. And also, we may, without loss of generality, consider only diagrams that don't contain any free cycles. If you just take the trace of the identity map, that's a free cycle, and it adds just a scalar to your interpretation, and it messes up the proof without actually, but it's very difficult to, I mean, it's easy to, if you prove the theorem without the trivial cycles, you just stick it to the trivial cycles. So you will just ignore trivial cycles. Okay, so technically speaking, when I say things like an equation holds between terms, blah, 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 of course I have to be a little bit more precise. when we write down these equations, I'm using some variables, right? So I assume here that I have a given set of variables denoting objects, such as A and B, and a given set of variables denoted F and G, and so on, denoting morphisms, and that each of these variables has a specific sort, meaning it's of the form, like every F goes from, say, A tensor B to C or whatever. Like every F has a specific domain and codomain, and then I can write down terms generated from those variables and composition and tensor and trace and dagger. Right. So this is just sort of a way of trying to make that more precise. And then we call this kind of thing a signature of dagger one-hot categories. I should have just made it slide all together. Okay, here's an example of a diagram. So notice that, for example, there are two boxes labeled F. This one is actually labeled F dagger, which is a mistake in the notation. It should just be F, but with the box in the upper right corner. And of course, you can have, in general, you have a diagram with many boxes. Some of them could be labeled by the same variable, and some of them could be labeled by different variables. This means if you interpret this diagram in Hilbert spaces, now what we have to do to interpret this diagram in Hilbert spaces, for each object variable, you have to pick a Hilbert space. So you have to pick a space A, which could be, say, a 5-dimensional space, and a space B, which could be a 7-dimensional space. Then for each variable, for each morphism variable, you have to pick a particular linear function, right? And then you have to interpret, and the point is if the variable occurs several times, then you have to always use the same function in those different places. And if F dagger occurs, you have to use the adjoint. And how do you actually, this whole diagram will, if you have chosen all that information, then this diagram will determine a scalar, right? And how you calculate the scalar is by the summation over internal indices. Right? That's the same diagram. And once you've chosen, so I actually wrote this down, but I've already said it. Right? For each A, you choose a Hilbert space. For each F, you choose a linear function, and then this determines a scalar, which is given by the usual summation over internal indices formula, or paths, or whatever. Right? So I've labeled the wires just for clarity 1, 2, 3, 4, and 5, so you can see what each index in the summation corresponds to a wire in this diagram. Right? And you're summing over all the possible sets of assignments for the type indices. Right? So of course you have to have chosen a basis for each space, but the summation is independent of the basis that you've chosen. And then for each, like suppose A1, B2, B3, A4, and A5 map to some particular vectors, then for each such assignment of vectors you have to evaluate the diagram, so you have to multiply the matrix entry of F, the matrix entry of G, and the matrix entry of F dagger corresponding to those particular basis elements. And then you sum them all up. Right? That's how it's done. Now to prove the main theorem, we're actually going to prove something stronger. It's called relative completeness. So remember, what I have to do is, given any diagrams M and N that are not isomorphic, then I have to actually find an interpretation of finite-dimensional Hilbert spaces that gives me a different scalar for the two diagrams. And here I'm going to prove something stronger, namely that the interpretation that I have to choose only depends on M, but I can make it independent of N. So, given a diagram M, then there exists an interpretation depending only on M, such that for all other diagrams N, this interpretation equals that interpretation if and only if M and N are isomorphic. So it's stronger because one interpretation will pick out M and distinguish everything else from it. Of course, you can't make it independent of M. I mean, you can't just have one interpretation that would distinguish all diagrams, because why not? I think that's obvious. You can't have that. Why not? Anyway, so we call this interpretation the M interpretation. Now here's a different diagram, different from the one on the previous slide, and it's called M. The other one was called N, right? And I have to now explain how this M interpretation is defined. And actually, it's sort of embarrassing. It's really very simple. The whole proof is very simple, right? Which is why it fits in half an hour. So here's how we're going to define this canonical interpretation of the diagram F. Remember, first, there are two variables here, A and B, right? So I have to pick two Hilbert spaces. Now I'm going to count how many wires are there in this diagram that are labeled A. And there are three such wires, namely wire number 1, wire number 2, and wire number 4. So for A, I'm going to pick a three-dimensional Hilbert space. And I'm going to also choose a basis for that three-dimensional Hilbert space, and essentially I'm going to identify the three basis vectors with the three wires. And for B, I'm going to choose a two-dimensional Hilbert space. So take a space whose basis is in one-to-one correspondence with the wires in this diagram. So of course I have to do a kind of free construction, so you would expect something like that. And then now I have to say how to interpret F and G. Okay, that's the more tricky part. So the same diagram again. So I have to. So first of all, I'm going to notice that in this diagram I've counted the wires 1, 2, 3, 4, 5, but I've also labeled the boxes X, Y, and Z. Because in general there will be more than one box labeled F, but sometimes I have to speak about this specific box. So it's going to be called the box X, and it's just a numbering of the boxes, right? But now what I actually will do is, for these three boxes X, Y, and Z, I will choose three algebraically independent transcendental numbers X, Y, and Z. If you want, you can just work in a, you can just call X, Y, and Z variables. Or I can call them transcendentals. So algebraically independent means that X, Y, and Z will be some irrational numbers that don't satisfy any polynomial equations with integer coefficients. So more specifically, since these are complex numbers, what I mean is that there's no polynomial P such that P of X, Y, Z, and X bar, Y bar, and Z bar is equal to 0 with integer coefficient other than the 0 polynomial itself. So pick these transcendentals, and now at first we're going to define three linear maps. That is the trick here. At first I'm going to define three linear maps, one for each box, and then later I have to say what the map F is, right? And it has to be the same for this box. So it's a two-step process. So first I'm going to define the F sub X map, and it's defined like here. So remember that this is going to be a map from the B space to the A tensor A space. So from a two-dimensional space to a nine-dimensional space in this case. And what I will do is I'll simply write down the matrix for this map, which is I guess a 2 by 9 matrix, right? Maybe 9 by 2, I'm never quite sure. And this matrix is going to have zeros everywhere except in one place. And the one place where it has a non-zero, it's going to have this transcendental X. Okay? And this X is going to be put in precisely the location where, there's this incoming wire here, B, and it's wire number 5. So there's a certain basis element of the vector space here called B5, right? And this vector space has a basis element called A2, and this vector space has a basis element called A1. And exactly these basis elements are going to make the matrix entry X, and then everything else I'm going to make it 0. So that the matrix will actually encode the information of which wires are connected to F in which places. So that's what's written here. And I do the same thing for Y and for Z. Right? So now I have defined three matrices, but I really only needed two. So the next thing I'm going to do is to define the actual F matrix. I'm going to simply add the matrices that come from the two occurrences of F. And I have to make sure that the one where F dagger occurs, actually I have to take the adjoint, which means it's the matrix with all zeros in it, and it has a Y bar somewhere in one particular place. And for G in this example, there's just one matrix, so we call it XZ. So I'm not giving the general proof, I'm just giving the proof in this example, right? Because it's clear how it can work in general, but it's also clear that you just need a lot of notation to actually be able to say these things, and it's actually done in the proceedings. So this is how the M interpretation is defined. And now we have to verify that the M interpretation of some other diagram N is equal to the M interpretation of M, if and only if M and N are isomorphic. Clearly, if they are isomorphic, then the interpretations are the same. That's trivial, right? If you interpret the same diagram twice, then you get the same scalar as the answer, right? Because you're summing over the same up to a reordering of indices or something. But we need the opposite direction. So I've written both diagrams. The M diagram from which the interpretation was defined with the x, y, and z in it, and some arbitrary other diagram that we want to. So we want to calculate the M interpretation of this diagram N. Right? If you check, you will. You probably have already checked that in this example, these two diagrams actually are isomorphic, because that's pedagogically better in this case, right, to prove my point. But you should think at this point of N as just some arbitrary diagram. So what happens when you calculate the M interpretation of N? Well, again, this is the same summation over indices formula that would work for how we would calculate the interpretation of N under any arbitrary interpretation, right? But now we use the M interpretation. So you're summing over a bunch of matrix indices, and at this point I will remind you that all these for this particular interpretation, all the matrix indices are either 0, or x, or y, or z. So what's calculated here is actually or x bar, or y bar, or z bar, right? We took the dagger sum place. So what's written here is actually going to be a polynomial with integer coefficients, actually non-negative integer coefficients, in x, y, z, x bar, y bar, and z bar. And I can point out that this is actually a homogeneous polynomial of degree 3. Because every summand of this polynomial is either 0 times something, or it's a product of 3 variables, for example, z times x, or z times x bar, or z times x times y. Of course, the degree of this polynomial is always equal to the number of boxes in N. So clearly, if N has a different number of boxes than M, then that would already be enough to distinguish M and N from each other. Because two polynomials of different degree can't be equal. And then when two polynomials are different, then you can find some non-brute, right, and find some actual numbers there. Anyway, no, actually, since they're transcendental, then the actual scalars would already be different. So now what I claim is that, so look at this polynomial. Now it has many different coefficients, say at x, y, x, and at x, y, z bar, and so on, but it's the coefficient at the monomial x, y, z that I'm interested in. And I claim that this coefficient is non-zero if and only if n is isomorphic to n. And to understand why that is the case, you just have to think about what the summation over indices formula actually does, right? How do I get a non-zero coefficient at that polynomial? That means somewhere in the summation, one of the summands here must have been x, y, z, right? But I don't know if it's been x, y, z, or x, z, y, or y, x, z, right? I don't know that, but I know that there has to be x, y, z in the summation formula. And that means there has to be at least one assignment of basis vectors to these wires 1, 2, 3, 4, 5, with the property that it fires at this box in x, at this box in y, and at this box in z, or at this box in x, at this box in y, and at this box in z, or any of the other permutations. And it turns out in this example that the only non-zero contribution that you get comes from the assignment where to the first wire here you assign the basis element A4, which corresponds to the fourth wire here, right? To the second wire here you assign the basis element B3 and B3 to B5, A4 to A1, and A5 to A2. So just a choice of basis vectors for the indices already corresponds to a function from wires of this diagram to wires of this diagram. And now, of course, if you check what it means for how can this matrix entry be an X, that can only be if the wire connected here, and the wire connected here pick out the X entry, and they can only do that if they correspond exactly to the wires connected here. So effectively, a non-zero entry at x, y, z is an isomorphism, because it's a function from the wires of this to the wires of this, and from the boxes of this to the boxes of this, with the property that it's a bijection from the boxes of this to the boxes of this, because you have to get x, y, z, and not, for example, x, y, y. And with the property that it then already follows that it's also bijection on the wires. Right. and that it preserves all the incidences of the boxes and the wires, and therefore it's an isomorphism. It's a little bit hand-waving, but in fact you get something slightly stronger. The integer coefficient is non-zero if and only if the two diagrams are isomorphic, but in fact the integer coefficient is equal to the number of different isomorphisms from n to n. So typically 0 or 1, but if there are non-trivial automorphisms, it could be higher than 1. Okay, now I said this theorem for the complex numbers, so Hilbert spaces over complex numbers. It would work over any field of characteristic 0. And you do that just by passing, if you don't have transcendentals, you just pass through a field where you've added the transcendentals, and then at the end you can remove them again. And now finally I want to say there's this open question whether the same statement is also true in bounded dimensions. So if I have two non-isomorphic diagrams and I want to separate them in Hilbert spaces, my proof uses unbounded dimension because the dimension is sort of proportional to the size of the diagram. We know that the result does not hold in dimension 2 because there's this counterexample due to Bach-Perret. So if you look at this trace of this product of 6 matrices and the trace of this product, they're always equal for two-dimensional matrices. It's an easy consequence of the Cayley-Hamilton theorem as a certain theorem. But of course it's a counterexample to completeness, right? Because that trace is really just, it's a diagram. And we don't know if it holds in dimension 3. I'd like to thank Gordon Popkin for making me work on this and cooperate for the counterexample, and that's it.
Any questions?
If you didn't have transcendentals, then reading, I've read what you've said in your abstract. So there's one theorem.
Right. So lemma 2 was the one that said I can pick the interpretation so that it depends only on m. And that fails when you don't have transcendentals.
There's an obvious example of taking, say, the algebraic complex numbers and sort of filling out and then seeing you can't at that level.
Where you can just take Q adjoint the square root of 2 or something like that. That doesn't have any transcendentals. Right? But the point is that you can of course adjoin the transcendentals. That will make lemma 2 true for this field. Then theorem 1 will be true for this field. And finally, when theorem 1 is true for this larger field, for two diagrams you found two different polynomials. Then if you have in a field of characteristic 0, every non-zero polynomial has a non-root. So you can then at the end pick some elements of your field that probably aren't transcendental, but that make that particular polynomial not equal to the other one. So that always works, just in characteristic 0. Oh, I think my battery ran out. Yeah.
Okay. So
Perfect timing.
let's thank the speaker again.